Okay, so we will learn to calculate derivative of a vector from different frames of reference. We will start with the easiest one. One will always be the ground reference, this one. So this capital X, Y, Z will be the ground frame. Another frame will choose a moving frame. So this small X, Y, Z will be the moving frame. So we will deal with various cases. Now, first case, suppose a vector. So this vector A is fixed in frame small x, y, z. That is the moving frame. Okay, so this is case 1. Okay, vector A is fixed in frame small x, y, z, the moving frame. So this small x, y, z is a translating frame, a translating reference frame, right? So to calculate, so we have to calculate this dA dt, that is dA by dt is time with respect to this ground frame capital X, Y, Z. Okay. So I'll continue in next page. Right. So this was the ground frame, capital X, Y, Z ground frame, and small x, y, z is the moving frame, or we can take it parallel or may not take it parallel. Just for the time being we are taking it like this, x, y, z, and say this you can consider a person at rest. This person standing on platform, and this moving frame, as it is a translating frame, you can consider this person moving inside a train or a car. Simply it's translating. So this person is a frame small x, y, z, so it's translating. Right. So now we have a vector A. You have a vector A which is fixed in the frame small x, y, z. So obviously dA dt with respect to small x, y, z is equal to 0. Now let's see how this vector changes with respect to capital X, Y, Z. So capital X, Y, Z, this person, at a certain time this person will see the vector here, and at a later time the vector will shift here as it's translating. See, as the vector A is fixed from this frame is translating. So that means the vector is also translating. If this is moving at a speed u, this vector is also translating at a speed u, at a velocity u rather. That is why this vector is fixed from this moving observer. So with respect to the person in ground frame, this vector is a translating vector, and you know, is this vector and this vector same or different? As a vector has translated, does it change? No, it doesn't change. So dA dt with respect to capital X, Y, Z is equal to 0. So that was pretty simple, that translating vectors don't change because they have same magnitude and direction. Now next case, we'll will be, the first case was both were, now okay, x y. Now next case we will consider vector A fixed in small xyz frame, okay, and obviously capital XYZ is ground frame. Now small xyz is a rotating frame, rotating frame with angular velocity omega vector. So this omega vector, you know that how to determine direction of the vector is given by the right hand thumb rule. So if this is the direction of the angular velocity, there it is, this is the direction, then the vector is pointing towards the thumb, this is the omega vector. Okay, by the way, so let's draw the frames. This one will be fixed always because this is a ground frame. Capital XYZ is a ground frame and the small xyz is a rotating frame. So suppose this you can consider a person stand still on ground, and this is a rotating frame. So you can take a rotating turntable like this, that's a rotating turntable, and it's spinning around with angular velocity omega like this. Yeah, so this person also spinning around, and so does this frame, this small x, small y and small z are spinning around. So the angular velocity vector is upward, omega vector is upward. Okay, now you have a vector A, right? This vector A is fixed in the xyz frame. Now, so if you differentiate the vector from this small xyz frame, you will get 0 obviously, right? So d a dt with respect to small xyz is equal to 0. Now we will differentiate this vector with respect to this capital XYZ frame, and let's see how it spins, how it varies with respect to the capital XYZ frame. There it is, x, y and z, and that's a vector at a certain moment. So this is the vector A, right? Now as it is spinning, angular velocity is given, so it rotates like this, so it's forming the slant surface of a cone. This angular velocity vector is upward. So if I draw this diagram, see, here it is. So at a certain moment, this is the vector A, right? At a certain instant t, this is the vector A. After a certain instant, this vectorially it will be A plus dA. I mean with respect to this capital XYZ frame. So this is the change. So the change is dA. Now, so this change happens to be dA, and see, there you get an angle, a small angle d theta. There it is, a small angle, this one, this much angle is d theta. Okay, right? So we'll draw another figure for it. I will draw the top view of this, how it looks from the top. From the top, this this is a circle, I mean this, you are looking at this circle, right? Suppose this angle is phi, say this angle, the semi vertical angle of the cone is phi. So here you see there, this point is tip of this vector A, right? Okay, so how about this length? This length is A sine phi, and see this is a vector dA. Okay, so that's also A sine phi because the magnitude doesn't change, and this angle happens to be d theta. Okay, so what about dA? What is the magnitude of dA? Let's draw it again. There it was A, after a small time A plus dA, so that's dA. Okay, now this semi vertical angle of the cone is phi. While I am looking at the top view, this is A sine phi, that is also A sine phi. This should be small, very small, and this is angle d theta. So and that's dA. Okay, so what is the magnitude of vector dA? Magnitude of vector dA is A sine phi multiplied by d theta. Now what is the magnitude of dA by dt? That's A sine phi multiplied by d theta by dt. So what is d theta by dt? It is nothing but the angular velocity omega, right? The angular velocity at which this vector rotates, this vector A rotates. So it's like this, right? This vector A from the ground frame rotates like this, right? So we are looking at the top view. See, this is the center, this is the axis of the cone, and it rotates like this. Okay, so this length, obviously this length is A sine phi. Okay, so you can write this A sine phi omega, right? So see, vectorially its dA dt is it is omega cross A. By the way, it's the cross product, it's the see, it's omega and A vector. If you see, this A vector is here, A vector in this diagram, you see A vector is here and omega vector is there. The angle between these two vectors is phi. So obviously it's mod of the cross product between these two vectors and omega, right? Did you get it properly? See, another diagram. This is vector A and this is the direction of the angular velocity of this vector omega, and the angle between the vectors is phi. So dA dt is omega cross A. It matches with that because see, in this diagram this omega is in this direction out and A is there, sorry, A is there, right? A is there. See here, omega, this is A, so omega cross A is this way. There you get this dA vector, right? So dA dt is this, or rather you can write dA dt with respect to this capital XYZ frame or ground frame equal to omega cross A. So that is one more case. Remember, this vector A is fixed in small xyz frame. Angular velocity of the small xyz is omega. So then this is the relation between derivatives of vector A in the two frames. Now our next case will consider here say A is fixed in a small xyz frame, okay, and small xyz is rotating at omega and also translating, you know, from Chesel's theorem, you know, you can combine translation and rotation. So that means you can think like this. I mean, this frame is rotating as well as translating. So actually it's doing like this, it's moving like this, right? Rotating as well as translating. So according to Chesel's theorem, you can superpose it into translation and a rotation. Translation at a velocity of this point, say, and translation at a velocity of this point plus rotation about this point. So this is I hope you know Chesel's theorem. So A is fixed in small xyz frame and small xyz is rotating and also translating, and capital XYZ is ground frame. Okay, now to calculate dA dt relative to capital XYZ. Now here in the solution, obviously you will get what you have got in the case 2, because why? This translation doesn't matter, so you can superpose this case as it's a superposition of translation and rotation. So you know, in the first case we have studied, due to translation dA dt is 0, it doesn't change. Due to rotation it changes. So just simply you can substitute the result what we have got in the second case. Let's draw at XYZ. This is the ground frame and this frame, it can be tilted also, doesn't matter. So this small xyz, so that's translating as well as rotating. So angular velocity is omega and say translating velocity is u, and A is fixed in xyz frame, so dA dt with respect to small xyz is equal to 0. Therefore dA dt with respect to capital XYZ is omega cross A. Okay, now this case is different. So by the time we know that this due to the translation of the small xyz frame, it doesn't matter, so we will just neglect the translation. So what matters is the rotating frames, at least the vector which is fixed in xyz frame, small xyz, doesn't change due to translation. So next case here, say A is not fixed, A is not fixed in small xyz frame. Now its rate of change in small xyz frame is this, obviously dA dt with respect to small xyz. Okay, so we'll consider this small xyz as rotating frame. Small xyz rotates with angular velocity omega, and capital XYZ is ground frame. Okay, now to find dA dt with respect to capital XYZ, this is our job now. Okay, So now let I, j, k and small I, small j and small k be. So I am not putting cap. If you like, you can put, right. These are unit coordinate vectors. Unit coordinate vectors in capital XYZ and small xyz frames. This will be needed. Okay, now let's see this dA dt. So in small xyz frame, vector A you can write as a1 I plus a2j plus a3k, right, where this a1, a2, a3 are components of the vector A with respect to small xyz frame. Okay, so dA dt with respect to small xyz is equal to, so dA1 dt, I'll write it as, see it's only magnitude, so I can write a1 dot, right. Dot means it's a rate of change with time. See dA1 dt is a1 dot. This is a shorthand notation. So into I cap plus a2 dot into j cap plus a3 dot into k cap. Or I'm not writing the caps on it. Okay, so that's it. Derivative of the vector A in the small xyz frame. Now derivative of this vector in capital XYZ frame. See capital XYZ. So that will be dA1 dt capital XYZ into I cap plus dA2 dt capital XYZ j cap plus dA3 dt capital XYZ k plus, again see it's this I is not a fixed vector in capital XYZ frame. So this will be di dt with respect to capital XYZ plus a2 into dj dt respect to capital XYZ plus a3 into dk dt with respect to capital XYZ. Now see, therefore dA dt with respect to capital XYZ, see it is this a1 is the magnitude only, so magnitude changes in the same way with respect to the two frames. So here I can write a1 dot into I plus a2 dot into j plus a3 dot into k plus, this is a real thing. Now di dt with respect to small xyz, see what will be that. Now we will use the result that if A is, suppose if a vector, say if a vector B is fixed in small xyz frame rotating at omega, then dB dt with respect to capital XYZ is omega cross B. Now we will replace replace B by I. So we replace B by I because I or I cap is a vector fixed in the small xyz frame, because obviously it is the unit coordinate vector in the direction of small x axis. So we can write di dt with respect to capital XYZ equal to omega cross I. Right. See it again. Di dt respect to capital XYZ is omega cross I. There. So replace this term. See, di dt with respect to capital XYZ. You get omega cross I plus, as this term, dj dt with respect to capital XYZ. What will you get? It is omega cross j plus a3 into dk dt with respect to capital XYZ is omega cross k. Now this is the term, this is the huge term we got by differentiating the vector A with respect to the ground frame capital XYZ. I'll just put it together in next page. So therefore dA dt with respect to capital XYZ is see this first term a1 dot I cap plus a2 dot j cap, this term, right? This term, this whole term is what? See, is written over there. This whole term is dA dt with respect to small xyz. So we'll write that dA dt with respect to small xyz. I hope you followed this, right? This term. See, here we have written dA dt with respect to small xyz is this term. Here differentiating A with respect to capital XYZ, you get such a term. This thing, this whole thing is this. So that's dA dt plus with respect to small xyz plus this term we can write omega cross this a1i, right? That's a scalar a1, right? Omega cross a1i plus omega cross a2j plus omega cross a3k. Okay, so therefore dA dt with respect to capital XYZ is dA dt with respect to small xyz plus omega cross a1i plus a2j plus a3k. This is nothing but the vector A. So we can write dA dt with respect to capital XYZ is dA dt with respect to the moving frame plus omega cross A. Now this is our final expression. We will use that many a time. So I'll decorate this, put a nice border around it and keep it for future use. Preserve this equation very carefully, because in our next lecture we will prove Coriolis force, that is the different types of forces in the rotating frames of reference, right? See, just note one thing, that the translation of small xyz frame doesn't matter. So it holds for this rotating and translating, say this capital X, Y, Z, and this can make it tilted also, doesn't matter. Small x, y, z, say it translates and rotates also. Angular velocity this way, angular velocity vector is this way, omega, and suppose there is a velocity of translation, it doesn't matter. So if a vector A changes according to this in the small xyz frame with respect to capital XYZ or ground frame, it will change according to this expression. It is rate of change in the moving frame plus this term.